Alrighty, it's exam one. Phys102, spring 26, have an electric field at point A. I'm just going to go ahead and draw my coordinate system there and then draw the vectors at that point A. The vector E1 is going to be in this direction. So that's E1, and then E2 will be in that direction. And then I also want to find any angles. My triangle right here. This side's 3, this side's 4. That means that this side is 5. That is, the square root of 3 squared plus 4 squared is equal to 5. And then I can find this angle right here, the inverse tan of 4 over 3. That's equal to 53 degrees. That means that this angle is also 53 degrees. Okay, so that's part A. And then for part B, I want to find the for part B, I want to find the x and y components of that vector. In order to do that, I need to calculate what E1 and E2 are. So B, I first find E1. E1 is equal to KQ over R squared. That's going to be 9 times 10 to the 9th times Q, Q1, which is 25 times 10 to the minus 9, divided by the distance, which is 5 squared. And I do it so that these cancel and that cancels, and it leaves me with 9 newtons per coulomb. And then in a similar way, I can find E2. E2 is 9 times 10 to the 9th times Q2, which is 32 times 10 to the minus 9. Remember, don't use that negative sign there. Divided by 4 squared. 4 squared is 16. 16 goes into 32 twice. Those cancel. And that gives me 18 newtons per coulomb. So I know that this one is equal to 18, and this one is equal to 9 newtons per coulomb. And then I want to find E1x. I want to find the x and y components of each. So E1, sorry about that, y'all. E1 x is equal to 9 cosine of 53. And 9 cosine of 53 is equal to 5.4 newtons per coulomb. And then I can find E1y in a similar way. That's equal to 9 sine of 53, which is 7.2. And then for E2, E2 only has a y component, and so I'm just going to label that as E2y, and it's equal to 18 newtons per coulomb. All right, I think that's it for part B. And now in part C, it continues on to find the magnitude of the electric field. I'm going to do that down here. It doesn't really matter like how you label these different parts, just as long as you have all these different steps. To find the magnitude, I like to draw a picture here so that I get all my components right. I know that this is now 18. I have 5.4 in this direction, and then 7.2 in this direction. So if I combine the two y components, I now get 10.8 and 5.4. I've kept an extra sig fig there. If you did 11, that's fine. Okay, so that's in newtons per coulomb for both of these. And now to find the magnitude of that, I say the square root of 10.8 squared plus 5.4 squared. I get 12. Yeah, 12. Sorry, y'all. I have a new computer here, so it's not. Anyway, that's equal to 12 newtons per coulomb. So that's the magnitude of it. And then I also want to find the direction. So if this vector is right here, I want to know what is this angle. That's relatively easy to find. It's first quadrant. It's just the inverse tan, or the opposite over adjacent. That's 10.8 over 5.4. That's going to be, I get 63 degrees. And that's the angle that I want, because that's the angle that is above the positive x-axis. Okay? And then that's second part, the second big answer I'm looking for. And then finally, I want you to find the potential. So find what is the potential at that point. That potential is going to be the sum of the two potentials. And the sum of the two potentials are going to be 9 times 10 to the 9th times Q1, which is 25 nanocoulombs, 25 times 10 to the minus 9, divided by the distance. The distance of that charge is 5 meters, plus 9 times 10 to the 9th, times the second charge, which was 32. We do include the sign there because this is a scalar quantity and that sign is important, divided by the distance, which is 4. These are not squared. Those go away. This cancels with one of those, and 9 times 5 is equal to 45, minus that goes into that, leaves an 8, minus 72. Is that 72? 9 times 8? Yeah, minus 72. And 45 minus 72 is minus 27 volts. All right, so that's that one. Now in this one, I want you to sketch 5 to 6 electric field lines for this configuration, use solid lines, and then sketch 4 to 5 equal potential lines. Notice here I have a 3 to 2 ratio. So if I have, say, 6 lines coming out of this charge, then I should have 4 of those lines are going to end because I have a 3 to 2 ratio. All right. So I'm going to draw 1, 2, 3, 4, but then I have 2 additional lines that just go out like this. And so now if you imagine, well, in this case, each line would be worth a half a charge, or 0.5 Q. And so I have 6 lines here that represent the 3Q, and then 4 lines over here that represent the minus 2Q. And then notice that they go from the positive to the negative charge. And then for equipotential lines, I want to sketch them in so that they're at every point they're perpendicular to the field lines. All right, something like that. Okay, what is here? I have proton moves from point A to point B. Electric field in the region is constant. What is the speed of the proton? Remember that potential is work, or we'll call it energy. I'm going to call it kinetic energy, actually, since that's what we're doing, divided by charge. It's energy divided by charge. And that this kinetic energy is equal to 1/2 m times the speed squared. So I can say then that 1/2 mv squared is equal to my change in potential times q. And then I just want to know what is v. All I've said here is that my energy is equal to v times q. All right, just solving that equation, this equation right here for kinetic energy. Then I can solve this for v. That's going to be 2 delta v q divided by m, and then the square root of that, that's going to be the square root of 2 times delta v. I'm going from 8 to -4, so that's a change of 12 volts. I'm not worried about the, well, I could put the negative in here. It actually is a negative change in potential, but then well, no, we're not going to worry about the negative. We'll just leave that out. And then because I'm just looking for the magnitude of the speed. And then the Q is a proton, so that's 1.6 times 10 to the minus 19 coulombs divided by m. For a proton, that's 1.67 times 10 to the minus 27 kilograms. I'm pretty sure that's right. I'm going to pause here. Yeah, that's right. do that, I get 48,000 meters per second. So that's part A. And then what is the electric field? Remember, we said that the unit for electric field is the Newton per Coulomb, but that 1 Newton per Coulomb is equivalent to 1 volt per meter. Then that should remind us of this relationship between the electric field and the potential. So E is equal to delta V over delta X. That is, when I have a change in potential across a region of space, it's because there's an electric field there. And if I want to know that electric field, I just divide that change in potential. In this case, it's going from 8 to -4, so that's 12 volts. I'm just looking for the magnitude here, divided by 0.3 meters, and then that'll give me the electric field, which is going to be 40 newtons per coulomb, or 40 volts per meter, if we want to express it in that way. All right, that's the free response. Let's look at the multiple choice. All right, these first couple were a little difficult, like you had to flex your muscles a little bit to get these two right. All right, I have this configuration of charges. I'm just going to draw a charge, a force that is repulsive in that direction. And now let's think about what is the force on the other. Let's write the equation, KQQ over R squared, because I'm looking for the force here, and that's the Coulomb's law, that the force is equal to KQQ over R squared. I have a charge that is 9Q at 3 times the distance. And notice that cancels out. So a 9Q is 3 times half the 2Q. Like if this was just Q, the 9Q would be, the 9Q is 9 times half the 2Q. So what that means is that the electric force vector is going to be half the length of this vector. Let me repeat what I just said. So there's my Newton's, or my Coulomb's law. My charge, the 9Q, is 9Q, and then it's 3D distance away, so 3 times this distance, which just, those two cancel out, the 9 and the 3 squared. Now, this charge is actually 2Q right here, so that means that the force that's acting on this charge right here is going to be half the force on this charge. Like if this was Q, it would be the same, but since it's not, this is going to be twice that. Okay, so that means that the answer is going to be D. That also carried on over into this one, that if I have a vectors like this, where this is F, and then this is 2F, and I want to know this angle, theta, then I just say the inverse tan of F over 2F, and that's, or the inverse tan of 1/2, is going to be 27 degrees from the positive x-axis. All right. Okay. 2-point charges of 4 centimeters apart experience force F. Now that separation is now doubled. So the force is equal to KQQ over R squared. If I double the separation, that means I get a factor of 4. So C is the right answer there. Proton and electron. So a proton with a big mass, an electron with a little mass are initially separated. They're not really that much different in size. I'm just sort of drawing them because they're different masses, which will experience the greater magnitude of force as they move towards one another. So they will both experience the same force because of Newton's third law, because of Coulomb's law, that they're both going to experience an attractive force. That attractive force, of course, is going to be the same. It'll cause the electron to move faster than the proton, accelerate more quickly, but the force is the same. All right, this figure shows two charged particles separated by a distance of 2 centimeters. What is the force on Q1? Well, that force on Q1 is in this direction, and that force is 9 times 10 to the ninth times 50 times 10 to the minus 6 times 1 times 10 to the minus 6 divided by 2 times 10 to the minus 2 squared. And the answer, if you do that, you get that it's equal to 1100. Number 5, yes, A. Even if you got your metric prefixes wrong, you would have gotten a 1, 1. So I know that the micro and the centi, you might have forgotten those, or you shouldn't have. But even if you did, you should have still gotten the 11 part right. And then you would have just realized that, oh, I just got the metric prefixes incorrect. All right, here I have Q2 has a magnitude of 6 coulombs. And I know that it's positive. And what is the sign and magnitude of Q1? I have one line here, I have 2 lines here. That means that this is 12 coulombs. And since they're coming out, it's going to be positive 12. At what point is the electric field equal to 0? So remember our general rule is we want to get as far away from the big charge as possible. So I'm going to guess it's either A or B. So let's just draw the vectors. We'll start at A. If I draw the vector from the plus Q, it's going to be in this direction, and the plus 4Q is also in that direction. So it can't be A. Let's just sort of see if it's B. Due to the plus Q is in that direction, and due to the 4Q is in that direction. And remember that E is equal to KQ over R squared. So notice here that this distance, if I call this distance R, then this distance is 2R. So I have twice the distance and 4 times the charge. So those cancel out. So those electric fields are equal and opposite to one another at that point. So B is the right answer. I could have guessed that, though, just based on that general rule that I want to get as far away from the charge as possible. What is the direction of electric force on this particle? The electric force is always for a positive particle, is always in the direction of the electric field. What is the direction of the electric field at point P? So I'll just start here and draw the electric field, go around clockwise. It's going to be, it's going to be in, sorry y'all, let me pause, I'm having computer issues. Okay, due to the minus Q, I'm going to have an attractive force in that direction. Due to this plus Q, I'm going to have a repulsive force. So the electric field is also away. Due to the minus Q, it's going to be in that direction. And then that's due to that one. And then due to this charge, it's going to be in that direction. So the net electric field is going to be to the left. All right, now I have 2 charges. I want to know the electric field at that point. The electric field due to this one is going to be in that direction, and due to this one in that direction. So that's the right answer, D. Right, these charges are separated by a distance x. What must be the electric field be for it to equal to 0? Well, I really like to do this just sort of by relationship. So if I'm going to draw my vector for the plus 2, that's E, I'll call that 2.0. And then this one is E18. So these two have to be equal. But look, if I know that this charge is 9 times, the other charge is 9 times, so I need a distance that's 3 times as far away. So this distance needs to be 3 times the 2 meters. So that would be a total of 6 meters. And so, not A, sorry. Not A, it should be 4, because 4 plus 2 is equal to 6. Okay. Another way that I could do that is I could just say that E 2.0 is equal to E18, and then that would be K times 2 nanocoulombs divided by 2 squared is equal to K times 18 nanocoulombs divided by R squared, where R would be this distance, the total distance, K's cancel, the nanos cancel. This 2 cancels with one of those 2's. And so R would be equal to 6 meters, the square root of 36, which is 6. And then that would be, this distance would be 6 meters. And so that means that this distance would be 4 meters. All right, which of these is a property of charge? It is quantized, it is conserved, it's not directional, it's not immovable. So B is the right answer. B here is negative. And so this is the net force. What is this? Which of these statements is true about A and C? Well, A has to be positive and C has to be positive because I need 2 vectors that go in these directions in order to get that. So they both have to be positive. There is no other configuration. So that's C. Problem with this kid is that she has an excess of negative charges. What is the potential energy? Is it positive, negative, or 0? Remember, potential energy is KQQ over R. Since R is the same for all 3 of these charges, like the separation between them, they're on an equilateral triangle, so they're all equidistant from one another. I can just look at the products of the charges. So this is not actually the potential energy, but it helps me to figure out if it's positive, negative, or 0. This is negative 6, negative 12, and then positive 18. And if I add up those 3 values, which represent the potential energy, I see that it has 0 potential energy, that there's no potential energy. Here, what is the potential at point A? Okay, so I'm going to make it a little simpler, by the way. I know that potential is KQ over R, but recognize that I have that N, which is 10 to the minus 9. I'm just going to leave out, well, I'll show you. I'll just write it out normal. Okay, so V is equal to 9 times 10 to the 9th times negative 8 times 10 to the minus 9 divided by the distance, which is 4, plus 9 times 10 to the 9th times 5 times 10 to the minus 9 divided by 5 plus 3 times 10 to the minus 9 divided by, what was that distance? 3 meters. So get a bunch of cancellations here. That cancels all of those. That gives me negative 18 plus 9 plus 9. Looks like that has a 0 potential at that point A. So A is the right answer. All right. Shows a map of equipotential lines. What is the magnitude of the electric field in this region? So my change in potential for these 2 points is going from 20 to minus 20, has a change in potential of 40 volts because it's going from 20 to minus 20. It's actually negative 40 volts, but I'm just looking for the magnitude of the electric field. And then X, change in X is 10 microns, or 10 times 10 to the minus 6 meters. And I know that, only for the electric field, that the electric field is equal to delta V over delta X. So that's 40 divided by 10 times 10 to the minus 6, which is 4 times 10 to the 6th. Which of these is a conservative? All right, 1 and 3 are the only conservative forces. And the unit of electric potential, it's an energy per charge. So that is joule per coulomb. I'll get rid of those little dots there. And then who is Dr. Young's favorite student? Well, all these are really great students, but of course, you are my favorite student. All right, tough exam, all right, but I trust you did well.